Uh, Welcome to this video where we will be looking at the capacitated facility location model with single sourcing. By single sourcing, we mean that all demand at a particular demand location has to be satisfied by supply from a single supply location. And single sourcing is a common thing that is used in many real life cases, and there are many reasons why single sourcing is used. It could be anything from union regulations to governmental regulations to consistency in production to various other reasons. So there are many reasons why single sourcing might be useful, might be mandated. So in the how do you manage, so how do you design your supply chain around that? That's what we're going to be looking at today. And we will here is an example that you can see that we'll be using. We'll set this problem up as a linear programming problem, and we'll solve it, and we'll see what the difference is between a regular capacitated facility location model and single sourcing capacitated facility location model, right? So Amos, reading through this, you will notice that, let me make the font slightly smaller so you can read most of it. So Amos is a company that supplies motors to ICC Inc. ICC uses these motors to manufacture ACs. Now, there are 4 locations where ICC can manufacture ACs, and the demand at these 4 locations in thousands of ACs is for 50, 70, 60, and 80. Now, Amos is considering building plants of building up to 4 plants that can produce these motors that go into the ACs that ICC uses. The plants, their production capacities and annual fixed costs are given here. So the 4 potential plant locations are in Denver, Atlanta, Chicago, and Tulsa. And the potential supply that you have at these 4 locations are 110, 130, 150, and 140, again in thousands of units, right? And these are the fixed cost values for those 4 locations. Now, the transportation cost for Amos on each lot of 1,000 units depends on which plant the lot is produced at, of course, and where it is being shipped to. And these are the transportation costs. So to ship one lot, which is 1,000 ACs from Denver to Boston, costs Amos 700 units. So Amos is bearing the cost of transportation also, right? That's what we have. So all ACs at a single plant must use motors that from the same source for consistency. So in this case, it's consistency. So if you're building, if ICC is building ACs in Boston, all the motors that go to Boston have to come from a single location. Now, that doesn't mean that, say, for example, if you build a factory in Chicago, which has a capacity of 150,000 motors, they can supply all the motors to both, say, Los Angeles and St. Paul's plants of ICC, because the only restriction is that all 60,000 motors in Los Angeles plants should use the same source, which is Chicago. St. Paul also uses the same source, which is Chicago. It's just that supply to St. Paul cannot be split between multiple supply sources, right? So that's the only requirement. With this condition, how do we formulate this problem? How do we solve this problem? How is it different from regular capacitated facility location model? So here we have to decide which supply locations are open. So which plants are we opening? There are 4 potential locations, and then we have to decide which of these plants is going to supply motors to which of the 4 demand locations. Boston, which of the 4 ICC locations, which are essentially our demand locations, right? Now, here the difference between this problem and the other problem is that here, if you decide that Denver is going to supply motors to Boston, then all the supply going to Boston has to come out of Denver, right? And the same goes with Dallas, LA, and St. Paul also. So in a sense, what we are doing here is we are taking one demand location, say Boston, and we are assigning it to one of the supply locations. And the same goes for the other demand locations also. So we'll take Dallas and assign it to one of the supply locations. Los Angeles is also assigned. Same goes for St. Paul. You're just assigning demand locations to supply locations, right? Now, what this does is here we don't have to keep track of how many units are going from, say, Denver to Boston. All we have to decide is Boston assigned to Denver? Because if Boston is assigned to Denver, all units going to Boston will come out of Denver, right? So all we have to decide here is which demand locations are assigned to which supply location, right? And that's how we're going to set up the linear programming problem. So I'm going to page. Right, there you go. So let's begin with our decision variables. So we have the similar kinds of decision variables here, but here the decision variables are going to be very are similar but different, right? So we'll begin with the ones that are the same, which is the y variable. So let's say we'll have y sub I. Let me. So we'll have y sub I, right? Which is the decision variable tells which of the plants are going to open, and y sub I is 1 if plant is open and 0 otherwise. Now, when I say y sub I, let's actually write this down. This can be y sub 1 right? So there are 4 potential supply locations, and so it'll be y sub 1, 2, 3, and 4. And these 1, 2, 3, and 4 are for the 4 supply locations, which are right? The supply locations are Denver, Atlanta, Chicago, and Tulsa. Right? So these are the 4 supply locations, and these are the 4 variables representing whether or not we are opening the plants at Denver, Atlanta, Chicago, and Tulsa. Right? So those are our y variables. So this is similar to the regular capacitated facility location model. Now we'll have the xij variables. So I'm going to say x ij, or you know what? Let's say x11, x12, x13, x14, right? Then we'll have x21, x22, 23, 24. Now here, when you say x11, the first one is the supply location, which is Denver. The second one is the demand location, which is Boston. So the supply locations 1, 2, 3, and 4 are here. Denver is 1, Atlanta is 2, Chicago is 3, Tulsa is 4. Demand location, similarly, Boston is 1, Dallas is 2, LA is 3, and St. Paul is 4, right? So we'll have x31, 32, 33, 34, x41, 42, 43, and 44, right? So these are all our decision variables. All of these are subscript. So as I make them subscript, let's talk about this. So these decision variables are going to decide which supply locations are assigned to which demand locations. Now, because we are only doing assigning of supply locations to demand locations, all we have to know is whether or not, say for example, Boston is assigned to Denver or not. So if Boston is assigned to Denver, all demand at Boston will be supplied by Denver. So here also the variable will turn out to be a binary variable, because all we are deciding is whether or not one particular supply location is assigned to a particular demand location or not. If it is assigned, then it's good. So if it is not assigned, then none of the demand at that location is satisfied by the supply location. So it's all or nothing. So given that that's the case, all of these variables are going to be binary variables, right? So these are all going to be binary variables also. That's good. Finally, that. I don't know, I'm spending too much time on that. Okay, so all the xij variables are binary variables. They will be 1 if supply location I is assigned to demand location J, right? So if supply location I is assigned to demand location J, then xij will be 1, otherwise there will be 0. Instead of saying they, I'm just going to say xij. Will be 1 if supply, or will be 0 otherwise, right? Okay, now so this is true for all the xij variables, right? So with that, we have our decision variables. All our decision variables here, every single one of them is a binary decision variable. None of them are continuous. Every one of them is binary. Okay. So with that, we have our decision variables. Now the objective function. So the objective function is going to decide. Obviously, there'll be two parts to the objective function. Let me do this as an equation. So the first part is this fixed cost portion. The fixed cost portion is going to be, this is for the supply locations only, so I going from 1 to 4, and you're going to add the 4 supply locations. So we know the fixed cost values, so the fixed cost values were given to us right here, 800,000, 900,000, 1.1 million, and 950,000. So you're going to multiply 800,000 times y1, 900,000 times y2, and so on. So actually, maybe I don't want to do it this way. So objective function, right? So it'll be 800,000 times y1 plus 900,000 times y2 plus 1100,000 times y3 plus 950,000 times y4. So this is the fixed cost portion, plus now we have the variable cost portion. So variable cost portion will be 700 times the number of units transported from Denver to Boston. But our decision variables here are not directly the number of units. If the value is 1, then the number of units will be all the demand at the demand location. So the way this will turn out, will be slightly different. So in fact, it might actually make sense to put it down as an equation. So the first portion was, let me, so we'll write this as a summation. Right, so we'll write this as a summation. There'll be, it's a double summation, so we can put the second summation in here. Right, so it's summation over all possible supply locations and all possible demand locations, right? So 4 supply locations, 4 demand locations will be 16 of them. So we'll multiply the variable cost value. So that is going to be Cij. So Cij times whether or not that particular supply location is assigned to the demand location. So that will be an Xij, right? Times the demand at J. So if the demand location is assigned to that particular supply location, then all the demand at the demand location is satisfied by that particular supply location. So it will be D sub J. Let me put that as a subscript, right? So that is basically how the second part of the objective function turns out. This is the first part of the objective function. So if I were to write it as one of these summations, I would put it down as summation of I going from 1 to 4, because there are 4 supply locations, right? The fixed cost, call it Fi, times the y variable, which is y sub I. So this portion here, the first portion here is this. So you know what, let me cut that. So let's write this as an explanation, which is equal to plus, right? So Cij, say for example, we write the first function, so 700. So it'll be 700 times, right, x11. So 700 times x11 times the demand at Boston, right? And the demand at Boston is 50. Now, why is this the case? Let's talk this out. So it's $700 to transport materials, one batch of 1,000 from Denver to Boston. $700 to transport one batch of materials from Denver to Boston. So by one batch we mean 1,000 ACs, right? Times whether or not we are assigning Denver to Boston to Denver, right? Whether we are assigning the Boston demand region to the Denver supply region. And if that's the case, if this variable is 1, which means that you are assigning it, then the 50 units that are going to Boston will come out of Denver. Otherwise, it won't, right? So that's the reason why. And similarly, there'll be other, all of these values. So it'll be 1100 times x12 times 70 and so on. So you'll have all of those numbers there. So I'm not going to write the whole thing out. Now let's look at the constraints. So again we'll have the same capacity constraints and demand constraints, and of course we also have the binary constraints, which are in this case will be all variables are binary. But let's write the capacity constraints or the supply constraints. Okay, so capacity constraints will be you can only supply a single demand location from a single supply location. So we'll say that x11 plus x12 plus x13 plus x14. This is from a single supply location. From a single supply location. Everything going out of a single supply location must be this should be equal to 1, right? Why? Because I'm sorry, no, that's the other constraint. So everything going out of a single supply location, you have to has to be less than or equal to the capacity at that supply location. So what is everything going out of the single supply location? So it's not just x11, it'll be x11 times d1. So in this case, it'll be 50 times x11. Why 50 times x11? If x11 is 1, which means that we have assigned Denver to Boston, then the 50 units to Boston will come out of Denver, right? 50, 70, 60, 80. So 50 times 70, 60, 80, right? So these are all the supplies going out of the supply location to the four demand locations. Now, if they are assigned, then the whole supply goes out. If they are not assigned, none of the supply goes out. But the total supply going out cannot exceed the capacity at that location, which is 110, right? Similarly, we'll have the next set of constraint, which will be very similar. So now that we have done this for Denver, we'll now write the constraint for Atlanta. So in this case, it'll be x21, 22, 23, oops, and 24. But again, remember that the 50, 70, 60, and 80 doesn't change because everything going out from the Atlanta region to Boston. If Boston is assigned to Atlanta, then all 50 units going to Boston will come out of Atlanta. So the 50, 70, 60, 80 remains the same. The capacity of Atlanta, however, is 130,000 units. So that demand will be 130. So similarly, we'll have two more constraints, two more capacity constraints here. I'm not going to write them, that's similar, so you understand those. Then of course you have the demand constraints. In this case, the demand constraint can be written to say that this is a single sourcing constraint, that all the supply coming into a particular demand location has to come from a single supply location, right? How do you write that constraint? We'll say x11 plus x21 plus x31 plus x41. So all the supply coming in from Denver, plus the supply coming in from Atlanta, plus the supply coming in from Chicago, plus the supply coming in from Tulsa. But these variables will tell you whether Boston is assigned to Denver, Boston is assigned to Atlanta, Boston is assigned to Chicago, or Boston is assigned to Tulsa. So these four variables, they'll either be ones or zeros, and all of these variables have to be equal to 1, which means that the Boston demand region has to be assigned to one supply region. It could be any one of the four, but it has to be assigned to one of these supply regions, right? So that's the constraint. So similarly, we'll have three more constraints here. Three more demand constraints. So this one is for Boston. We'll have one for Dallas, one for LA, and one for St. Paul, right? So now this video is already gone on much longer than I expected. So what I will do is I will post this as a formulation. I'll do the Excel solution in the next video, right? I'll see you in the next one. Take care.